In the last part of today's lecture, I'm going to discuss meta-reinforcement learning, how we can apply the concept of meta-learning to reinforcement learning tasks. So to define the meta-reinforcement learning problem, we're going to kind of operate by analogy. We'll first see how generic learning can turn into meta-learning, and then see how generic reinforcement learning can turn into meta-reinforcement learning. So as a reminder, generic meta-learning can be written as some function f_learn that you apply to a training set dtrain. Generic meta-learning can be written as minimizing the loss function on a test set by using some parameters phi I, which are obtained by applying a learned learning function f theta to the training set. So in the case of gradient-based meta-learning, f theta is just gradient descent from the initialization determined by theta. In the case of black box meta-learning, f theta involves running an RNN with parameters theta on dtrain to produce a hidden state. And that's what goes into phi I. Okay, so let's try to apply the same idea to reinforcement learning. We can write reinforcement learning like this. The optimal parameters theta star of your policy pi are obtained by taking the argmax of the expected value of the reward under pi theta tau. And we can say that this is FRL applied to M. What is M? Well, M is the MDP. So FRL might involve actually interacting with the MDP to generate some rollouts, which is quite different from generic learning, where we operate on a fixed training set. So the MDP here is a tuple consisting of states, actions, transitions, and rewards. Meta-reinforcement learning can then be defined as follows. We're going to find some parameters theta star, which are the argmax of the sum over n different meta-training MDPs, and for each of those meta-training MDPs, we're maximizing the expected value of pi phi I, where phi I is obtained by applying a learned learning algorithm f theta to the MDP mi. So it's very similar to generic meta-learning, only in generic meta-learning you had, for every task you had a training set and a test set. Now for every task we have an MDP mi, and we might actually interact with that MDP during the adaptation process. And our goal will be to find the best policy we can for a new MDP using the smallest number of interactions. And meta-training can reduce that number of interactions dramatically. It can reduce it from the thousands or even millions that we need with deepRL to just a few rollouts for every MDP after meta-training. The meta-training process itself might still require tens of thousands or even millions of rollouts, but the adaptation will be fast. Okay, so here's how we can set this up. We have our data set of our meta-training MDPs. Our assumption is that our meta-training MDPs come from some distribution P of M, and at meta-test time, our test MDP is going to come from that same distribution. Okay? So that's just like in supervised meta-learning. In supervised meta-learning, we have some distribution over tasks. We assume our meta-training tasks came from that distribution, and our meta-test tasks also came from that distribution. For meta-RL, we have the same assumption. We assume that our MDP came from some P of M, and our test MDP will come from that same distribution. That doesn't mean that we've seen mtest before, not at all. It might be an entirely new MDP. This assumption just encodes a structural similarity between the meta-training tasks and the meta-test task, and the structural similarity stems from the fact that they come from the same distribution over tasks. So some examples, maybe P of M corresponds to a distribution over different household chores that a robot might perform. So you sample a bunch of different household chores, you use them for meta-training, and then you would hope that that can generalize to new household chores from that same distribution. Or, in a simpler example, maybe you have the little half-cheetah benchmark, like the one that you guys played around with in your homework, and different tasks maybe might correspond to running at different speeds in different directions. And then at meta-test time, the cheetah might be asked to adapt to run in a new direction that comes from that same distribution. So of course the example up above is fairly complex. The example down at the bottom is really, really simple, and most of your meta-reinforcement learning problems will be somewhere in between these two extremes. Okay, so let's talk about the equivalent of black box meta-learning for meta-RL. So this is kind of, in some ways, the simplest kind of meta-RL. The main question you have to answer is, how do you implement f theta of mi? That's really the main thing you have to figure out. What should f theta of mi do? Well, it really needs to do two things. The first one is very similar to supervised meta-learning that we saw before. It needs to improve the policy with some data, and that data is going to come from interacting with mi. But there's another thing that it needs to do. It needs to, and this is new to RL, it needs to actually choose how to interact. It needs to choose how to collect the data that will allow it to improve the policy. So it needs to actually also choose the actions in your RL interaction loop. So in RL, every time step you get a reward and a state, and then you pick an action according to your policy. So meta-RL basically has to also choose how to explore. So it has two jobs now, not just one. So let's talk about the first one. That one's a little simpler. And we're going to basically adapt the black box meta-learner that we had before. Let's say for now it's just an LSTM. So the way that we can improve the policy using some experience is by reading in that experience the same way that we read those XY tuples from the training set in the supervised meta-learning case. So we'll have an RNN, and that RNN will read in each of the transitions and rewards that we've seen while interacting with MI. So it'll read in S1, A1, S2, R1, S2, A2, S3, R2, S3, A3, S4, R3, etc., etc. And there's many variants on this. I mean, the way that I drew it here, it's a little redundant because the next state is being read in twice, so you can simplify that a little bit. Right. But the point is that you somehow need to read in all of those transitions that you've seen from MI, and that gets you some hidden state, H, and that hidden state is used to predict an action for a new state. So this is exactly the same as the black box meta-learning that we had before, except that instead of reading in a training set consisting of X's and Y's, now you read in a training set consisting of S's, A's, and R's. Okay, so that's how we can do number one. And of course, theta star now corresponds to the parameters of this RNN. And you can think of this little last bit that takes in H and S as being pi phi IA given S. Just like with the black box meta-learner, that little bit at the end could be viewed as a classifier condition on HI. Here we have a policy condition on HI. And just like before, these phi's are just HI and the parameters of this little policy head at the end, which we're going to call theta pi. Theta pi, of course, is unaffected by the task, but it is meta-trained, whereas HI is affected by the task, and that's just the hidden state of the RNN. Okay, so what I'm going to claim is that if we set up a policy like this, and then we train it with RL on each task, it will actually also solve the second problem, the problem of learning how to explore. So do we just train an RNN policy? Well, basically yes. So here's the idea. Let's say that you have a very simple RL problem. So here we have this mouse, and it's going to explore this maze and find the cheese. So different MDPs will have the cheese be in different places. Okay? So very simple four-state MDP. I made it really small just so that I could visualize everything. And let's say that on the first episode, the mouse decides to go to the right. So now our RNN is going to read in the fact that you went to the right and you got a reward of 0. Then the mouse is going to choose some other action, maybe it decides to go to the left. So now the RNN will read in that the action is left and the reward is 0. And now the episode ends. Let's say the episodes are constrained to be only 2 time steps. The episode ends, but the RNN keeps going. So now there's another episode. The mouse starts off in the same place in the lower left corner and now decides to go up. So the change in color represents a different episode. And it gets a reward of 0. So now the RNN gets another step. Notice that the RNN didn't reset between episode boundaries. And maybe it randomly decided to go right. And now the RNN reads in that the action was right and the reward was +1. So now the RNN has seen that if you go left, you don't get a reward. If you go up and then right, you do get a reward. And now the episode resets. And now the mouse knows that it should go up because the RNN has that in memory. So it'll go up and then right again and get that reward, and so on. So crucially, the RNN hidden state, or the LSTM hidden state, is not reset between episodes, which is what allows the RNN policy to remember where it got reward and then revisit those places. As far as the meta-learning process is concerned, these 3 episodes together are one long meta-episode. So the actual reinforcement learning algorithm that's training this RNN thinks this was just one long episode where you happen to have been teleported back to the beginning repeatedly. And of course, once it's aware of that, it will figure out that what it should do is learn to explore, because that's what maximizes its reward for that meta episode. So just like black box meta learning in the supervised case reduced the meta learning problem to just another supervised learning problem one level up, in the same way, applying black box meta learning to the reinforcement learning case just involves taking the same RL problem but lifting it one level up, where now you're maximizing reward across episodes. So why do recurrent policies learn to explore? Well, it's basically because once you've seen these episodes and their corresponding rewards, you can figure out where the reward is. So there were 3 episodes there, but 1 long meta episode. And maximizing reward over the meta episode requires learning to explore. There's nothing special we have to do about it. RL will do it for us. So because we're maximizing the reward over these meta episodes, that's what causes this thing to learn how to explore. So this idea has been used in a number of prior works going back a very long time. One of the earliest that I'm aware of is this paper called Memory-Based Control with Recurrent Neural Networks from 2015, which had this kind of silly looking, they call this a water maze task. It's basically kind of like a 2D navigation task where you get a reward for going inside the red circle. And the different colors here show different episodes. So the pink is the first episode, and you can see that kind of wanders around. And then the blue and the cyan and yellow are the subsequent episodes which much more directly go straight to the goal, straight to the red circle. More recently, there were several papers, namely Learning to Reinforcement Learn from 2016 and RL Squared, also from 2016, that apply these ideas to learning to navigate mazes. So there, each episode is one attempt to traverse this maze, and each meta episode involves multiple attempts to traverse the maze. So if on one of those episodes you find the exit, then you can adapt to it later. So that's illustrated best probably in those pictures on the right side. So if you have some good behavior on your first episode, then you'll remember where the goal is and you can go straight to the goal in the second episode. Okay. Now there's been quite a bit of work on different architectures for doing this. Some of them are kind of inspired by sequence models, like I described before. Some of them are more inspired by things like transformers. One particularly effective architecture, which is actually simpler than standard sequence models, is one that encodes all the transitions you've seen for a particular MDP independently, and then just sums together their embeddings. So this is a little bit more like what prototypical networks does. And that also tends to work really, really well. Now we can also do gradient-based meta learning in the RL setting. So gradient-based meta learning in the RL setting works basically the same way as it does in the supervised learning setting. So regular reinforcement learning might involve, let's say if you're trying to teach the ant how to run forward, you might generate multiple episodes running forward and use them with, for example, policy gradient to update your parameters. With gradient-based meta learning with mammal, you have episodes running in all different directions, and just like before, you modify your parameters so that one policy gradient step of adaptation has the largest performance increase on its corresponding task. So exactly the same idea as before, applied to RL basically without modification. It takes a little bit of care to compute these second derivatives for policy gradients, so there's some fancy calculus and algebra that's needed, but the concept is basically exactly the same. Here's a nice kind of visual illustration of this in practice. If we run meta training with mammal for this little quadrupedal robot, and the tasks will correspond to running in different directions, then after meta training, if we just run the pre-update parameters before we actually adapt it to a task, it's kind of like running in place. It's basically trying to see, does it get more reward going this way or that way or that way? So it's just kind of running in place with small perturbations. And then after one gradient step of policy gradient, it actually immediately figures out if the reward is being given for running forward, it'll run forward. If the reward is given for running backward, then we'll run backward. So that's the basic idea. Okay? So just like with supervised meta learning, there are different types. The non-parametric thing is a little difficult to apply to RL, but there are black box or contextual meta learning methods, and then there are also gradient-based meta learning methods.